Okay, now finally, right, I just wanted to sort of quickly go through because go through this last thing, right, which is actually visual captioning. Okay, you would have seen it, you would have read about it, but then I thought, right, we'll just talk about it briefly. Okay, that's again a high level task, right? I mean, so all these are parts of high level vision, right? What we are doing now, which was the final part, and really, right, classical approaches and all, there is no point, right, talking too much about them, and most of them you can do now. They are all based on, like I said, right in the kind of beginning, they are SIFT based, or they are Haar wavelet based, or they are hog based, all those things that you know, right. But then thing is, they are not at all robust, they are not fast, they cannot run real time. Therefore, the whole focus is on actually deep networks. That's why for high level vision, right, I thought there was no point spending time again going back doing classical things and all when things have come so far. It's always better that you learn latest things, right, which are all deep network based, so that because even whatever you do will also be all typically deep network based. I mean, because classical have of course, they are good, but then beyond a point, right, I mean, they can only do so much, by the way, right. Now, image, this one, captioning, right. So I'm going to be very kind of brief about this. Okay, so what is image captioning, right? As we all know, okay, what we want to do, right? I mean, it's basically and kind of interaction between what we'll call as a visual feature and actually textual feature, right? Like a language. Now, until now, right, what we saw was only one sort of this one, right? This one, a modality, right? In the sense that it was just image all the time, or perhaps it was text sometimes, right. But then, right, here is a case where, of course, when we did RNN, we talked about it, right. At the time, we did flag this thing that you could have features coming from a visual feature coming, and then you could have this one, a textual feature coming, and then you have to combine them and so on, right. So now, so this image captioning, right, what does image captioning mean? It basically means that, right, if I give an image, then you should have a network that looks at that image and actually produces a caption for it, right, which should actually best explain what is happening in that image. But then, right, what happens is, even if I ask let's say individuals to do it, right, it won't be the case that what he says is exactly what I will say, or let's say what she says, right. It will not be the same, because she will think about it in a certain manner, she will write about it in a certain manner, I will write about it in a certain manner. That's why when they actually develop a data set, right, what they do is they ask multiple options. They give, like, for example, right, for each image there could be at least 5 to 10 different sentences, all of them are valid. So as long as you produce one of them, it's okay. It's not like you have to produce that sentence and all, and sometimes you can't even produce exactly that sentence and all. You'll produce a meaningful thing, hopefully, where it conveys what's going on. But then, right, what it conveys, it could be, right, any of those say 10 things, and again, when you give a new image, it will just pick up from whatever it has learned, it will throw out something. Okay. Now, so until now, right, all this we have done, right. So now, so what we want to do is, for example, right, I mean, in this case, right, it's not simply that that we are interested in object kind of, right, a detection or something, right. All that could also be potentially important for this problem, where we want to explain what's going on, because maybe it's useful to know that, right, that there is a person there. It's useful to know perhaps that there is water there. It's useful to know maybe to actually detect that there is an object there, which is a surfboard. So object detection could still play a role. It does play a role in these kinds of things. But then, right, this talk, right, is going to be at a much lower level. Okay, so what this means is that we want to have a description, and that kind of description will perhaps involve surf, will involve the ocean, will involve surfboard, will involve water perhaps, right. So you could think of multiple options. Here maybe it's about the car, it's about the trees, it's about the road, right. All these, you expect all of them to sort of come up when you want to say something about that image, and as opposed to fixed set of visual categories, right. So if you kind of look at what we did previously, right, when we did object detection, we are always talking about n classes, now whatever, right, n number of classes, always a fixed notion that we have in our head, maximum 1000, we don't even talk beyond that. But then vocabulary is not like that, right. Vocabulary is like whatever, right, right, millions of words, whatever, right, so many words there, tons and tons of words, and there, right, you cannot say that I can only have this many classes and all. So therefore, right, this fixed level of classes and all, right, we have to kind of we have to walk out of that kind of a mindset. And in this case, right, it's kind of producing, ideally, right, we want to say that a person is riding the surfboard in the ocean, and then for the next one we might say red truck is parked on the street lined with trees and so on, right. So we need a description that should be rich. Now again, right, as we said before, if you have image, right, we know that finally from an image we can capture features. Similarly, if you have a sentence which we know is made up of words, so we want to know, right, what kind of features can be associated with words, and that's what we talked about, what's called word to vec, right. When we did RNN, right, if you guys recollect, I talked about something called word to vec, which can actually give a word embedding. and a word embedding is needed because you cannot use a one shot vector for a one hot vector for a word, because it does not make sense, right, because words occur together in a certain way, and therefore, right, in that space, right, if two words frequently occur in a sentence, then they should be in that feature space, they should occur right somewhere right near to each other. It does not make sense. If you do a one hot, right, then one guy will be here, one guy will be somewhere else, whereas you don't even maintain that kind of, you don't actually, I think all this I talked about, right, when we did word to vec. So the idea is that you want an embedding which will actually capture the fact that certain words occur together or certain words typically come together in a sentence. All of that should be captured in that word embedding, right. That's what a word to vec does, right. I mean, you can do it using glove, whatever, right. Now, as far as an image is concerned, we know we can use AlexNet, you can use VGGNet, any of those in order to get our feature map representation, right. So the feature map again, right, again what you want to pick, whether you want to pick the final convolution layer feature map, or whether you want to the fully connected feature map, or whether you want to pick the convolutional feature map, depends upon what you want to do. See, for example, if you wanted to pay attention, right, attention is something that you have heard, right, deep networks with attention is there everywhere now. So what does it mean? That means what attention means, what that means, when you are generating something, you want this network to look at that region, you want it to pay attention to something, okay, which means that that network should be able to go and locate something there. If you give a fully connected feature map, it cannot do that at all, right. That is why when you want a convolutional feature map and when you want a fully connected feature map, depends upon whether you want attention or not. If you want attention, then typically it is a convolutional feature map, because that gives a handle for this network to go back, and so if it says that I am going to pay attention to a feature in that convolutional feature map, it means that in the image there is a corresponding region where it is paying attention. If it is a fully connected thing, nothing like that. If you pick something, it is the whole image, right. So again, attention and all when it comes, because captioning with attention is a very common thing, because you do not want to just throw captions like that. You should also pay attention to what you are looking at that time when that word. So for example, if a certain word has already emerged and I want to right, pick the next word up, I should pay kind of attention to what is there already with me. And then I should also pay attention to this new word, right. I mean, okay, right, which during when you of course train, right, when I train, I am also going to go to give the next word. Therefore, you want to pay attention, where is that coming from, right, what is there in that image in that region. So whether you pick convolutional feature map or whether you pick a fully connected feature map depends upon various things, including attention, okay. And of course, this is that word to vec thing. So what really do you want, right? You want a sentence to come out, right, which and normally when you train, you will train with lots of sentences. That is how training happens, right. So you have an image, so you should have kind of paired data. You should have an image, you should have of course, for that image you could have a bunch of captions, not just one caption. You could have a bunch of captions, and then you push this image, you give one caption, you push the same image again, you say maybe the other caption is also equally okay, right. Any one of them is okay. But then something like this, not see, for example, cat sat on mat, right, this we know is very likely to occur, therefore such a sentence should get a probability which is high. So this we are likely to see, right, anywhere you read, probably cat sat on mat is more common, mat sat on cat is far less common, right. So you want a probability for such sentences to be low. But then the point is, right, training a network with such a joint probability is not actually a good thing to do. So that is why what you can do is, you can actually give this conditional, right, you can arrive at this one, a conditional sort of a representation, because you know that you have a causal nature here, right. For example, after I produce the first word and actually pick the second word, the second word, right, depends upon what came earlier. The third word depends upon what came as second word and what came as first word. Of course, beyond a point probably it does not even matter whether you need to know what the first word is, but sometimes you can have a memory that can go really far back, right. Sometimes when we do this summarization of movies and all, right, somebody says rotten movie, he begins like that and then says something else at the end, but then you want to make sure that rotten thing what he said should still be factored in when you actually give some kind of a rating, right. So this connection, how far should I retain the memory and all, that's a totally sort of a different issue. But I am saying this kind of dependence allows you to split this probability, right. This is just joint, right, you can actually write it like this, and this is what exactly an RNN will do, okay. So for example, so what we will do is, instead of predicting a joint probability of the sentence, we will give kind of one word at a time, and then at each of these probabilities we would like to maximize, right. So we like to maximize the probability that word S2 comes out when I have seen S1, and word S3 comes out when I have seen S1 and S2 already, right. So that is exactly what an HMM will do, right. So here is where, what is this? Oh yeah, so basically, right, so here is how it will look. So for example, the first H0, right, I mean, okay, so right, this is an RNN, right? It could be an LSTM or whatever, and then you have an H0 here, you have an H1 here, you have an H2 here, and so on. So what this H0 will do is it will actually take the features from your CNN in this case, right, because it's an image. So this image goes in, so its feature map comes, and then that is fed, and then you give a start token. So start token is something, right, which you have to give. So which means that, okay, take this image, take the start token, and start something. And during training, of course, we know exactly what we want to say. We want to say the caption is straw hat, right? That's our caption. So we say straw should come out, which means that this H0, right, will get no, you will get an H0 based upon this feature map, these weights, and this input, which is start token, and whatever weights that are sitting there. Then you will output. Hopefully, you will output straw, right? That's the whole idea. And then there, of course, you have a cross entropy loss here because you have this vocabulary that you expect to come out, and then right, if that vocabulary doesn't come out, then there is a cross entropy loss. And then whatever is that word that came out of this, right, its word embedding will go next here, right? And now that it knows that the earlier word was straw, now of course, so the earlier information is coming from here, and then no, straw, okay, and then okay, the next work that you want is actually hat, right, which is what you want as output. And once straw and hat have come, right, you want it to kind of end, so you want to, right, put in an end token, and that's why the end token will come, right. So in a sense, this is what is going on, and this is exactly an implementation of this, right, where you are trying to, right, maximize the probability of a certain word, given that a certain number of words have already occurred. Now when you do this, so right, so the way you can see it is, for example, right, you won't take, of course, the last thing, right, you just take the fully connected feature map coming from here. So right, that's what you would kind of, right, push into H0, and then you given the start token, then out comes Y0, and then, right, Y0's embedding will go here, and then it kind of goes on, right, and of course this and all you've already done when we did RNN. Now after training, right, during kind of a testing time, right, what will happen? So a testing time, right, of course, I mean, so right, it'll start with a start token, and then it'll output something, and then when does it know how to end? When does it know how to end? So for example, in this case, we know it's a straw hat that should come out, right. So then what it'll take the start token, it'll take the image, of course, right, because that's the whole thing. It's going to take the image features, and then now for this it needs to produce a caption now, right. So it will kind of produce something, and then right, that will go in again. Hopefully it's a straw, and then hopefully it's a hat. And typically what happens is, right, because it's an RNN, right, there is nothing like a length, fixed length, right. You know that in RNN there is nothing like a fixed length vectors, right. So what it will do is, it will keep on producing words until it automatically hits the stop token, and that comes from whatever it has learned. So whenever it has seen many times straw hat and there is a full stop, then it will know that after hat it's over. Straw hat, it should be a full stop. Okay, sometimes that's why, right, that's why sometimes when it produces captions, you find that something is funny about that caption. It doesn't seem to end at the right point, so because it doesn't know where to end. It's not like a human, right, where you know that, oh, precisely end here, right. It doesn't know that. So it has to go based upon whatever it has learned, and then whereas if you have a transformer, I think you can do something better. You can fix the length and all, but here you can't do any of that. If it's an RNN, it will keep on producing until it itself encounters a stop token and stops there. So when we show these examples, it doesn't mean that exactly, right, that's the way it will happen, right. It doesn't mean that straw hat and full stop will happen. Okay, so for example, so if you look at a training data set, which is a Microsoft Cocoa here, so right, so somebody has done this work, right, 120,000 images for which captions 5 sentences each. So these are all humans that have written the captions. So for example, you can write 5 different things about this guy: a man riding a bike on a dirt path through a forest. Someone else says bicyclist raises his fist. So all of these are correct, equally correct, right. So any of these captions is okay. That's what we mean by there is no single caption, right? And finally the test caption, when you give this image or something similar, not this image, when you give something similar, it doesn't mean that you'll get one of these. It can still be a mixture of this, right, whatever right, it believes is correct. And as long as you're okay with it, right, you're okay with it. I mean, that's why, right, even to get a proper score and all, it's not easy in language. But you see, it produces a caption, you have to know whether the caption is good or bad, right. So for example, so here, right, I mean, it's done a fairly sort of, right, a good job. A group of people standing around a room with with remotes, which is actually pretty correct, right. It actually figured out that the remotes here. Then similarly, a young boy is holding a baseball bat, very good, right, during inference time. And then a cow, I think this was some scene from India. Cow is standing in the middle of his street, right. What to do? Now here is where it went, right, very bad. A young boy is holding a baseball. That's a toothbrush, right? Went totally wrong. And then a man standing next to a clock on a wall. Clock is correct, man standing is correct, but on a wall is really not correct, right? So again, so right, such failures can happen, and one of the reasons for these failures is that it's not paying attention, perhaps, right? Attention to things that it should pay attention to, right? Which is why image captioning with attention, right, is important. And with the moment you say attention, that then you are saying that it should also look at certain places in the image, from where, right, you should actually pick whatever information is needed, and attention cannot be supervised. There's no way to tell where you should pay attention to, right? When you look at something, do we go and do we all pay attention the same way? No. Each one has his own way of paying some attention. Right? We gather something important. So that's why supervision can only be on the words that come out. You cannot have a supervision on say attention. So what you hope is that the network will automatically pay the right kind of attention to actually produce the right word. And the way you incorporate attention is, of course, now you have changed your layers, right? See the feature maps, you have gone to convolutional feature map now automatically in the image domain, because now you want to know where you are, right, where to pay attention, and then what you do is on your feature map, right. So for example, so it's like this, right. What you will do is if you kind of think about the feature map is being divided into some grids. So what you'll say is you'll attach an attention for each of these regions. Okay, think of this as V1, V2, V3, and then you have an attention weight which is like A1, A2, A3, and so on. And therefore, what happens is, so this network, right, in addition to producing right whatever output it was earlier producing, which was a vocabulary, it should also produce the attention weights. What that means is the attention weights, right, will then be right taken through and then sort of right given as the input to your subsequent word. That means along with the word, it's also telling where to pay the attention. Z2 is actually a scalar. It's like summation AI Vi. So which will then mean that if it's a hard attention, right, what it will do is it will only have one non-zero AI, everything else will be 0. That's like a hard attention. A soft attention will mean that, well, you pay some attention there, but then pay a lot more attention here. So there are kind of different kinds of attention, right, within image captioning, and now the hope is that, right, so when a bird comes, right, it will probably look at this area, because in that image feature map, right, I mean, again, this is something that it should learn on its own. We can't tell, hey, that is the bird. It should know where the bird is, right. So that's why, right, when they train this network, in order to show that it's doing the right thing, they show this. They show that where is the attention. You can go and map it, no. See, for example, I mean, if I have a weight 0.1, I have 0.1, and then I have 0.7 here, everything else is small. If I go and map this region, right, where is the highest intensity for 0.7, hopefully, right, it should be on the bird at that time.
When this word bird pops up.
Yeah, right, when that bird pops up. So it's like when I kind of print that caption, right, the bird, at the time I should actually look at the attention. Where was the attention? Then it says bird sitting on the tree. Then when it comes to tree, at the time if you look at the attention, because that attention map is not this, that's gone here, no, somewhere here it will come, when the tree comes. At that time you should go and look at the attention map. Then you will see that, oh, it's looking at the tree. So that is a way to kind of convince yourself that it's doing the right thing, because you are not, there's no supervision. That is why it's thought that the wall should automatically come. Yeah. See, that's why, right, I mean, how to remove that bias, and there's a lot also to do with the data sets itself. If the data set has a bias, right, then it will learn all that bias, right? You can't help it.
Maybe if the data set included some image where the clock is on somewhere else, then
no, but then you will see that there will be some other problem. Then you would have missed something else. But then the hope is that on the whole it does something reasonable. On the whole, you should say, for example, right, so bird, right, so when this bird came, right, see the attention, right, where the attention is, right. So for example, flying, again probably, right, that has to do with the bird, therefore the attention is still there. And then body, so now you see that the attention is shifting to the water. And then when you come to water, right, look at, I think around the bird it's all fully water only. It may not precisely happen, but you can see that there is something going on. I mean, it can't be, you can't like hang the author saying that, hey, I mean, how come there is something on the bird and all, right? It will do something, but I think you can see the idea, right? But then right, something is still not there, right, which you would have liked to have, which is like see, one other thing, right, that you might want to do is, which are actually extensions and all, right. I mean, after this, so for example, right, so see, look at this, a large white bird standing in a forest. It's gone wrong, right? I mean, this animal, right, it kind of took it to be a bird, despite the attention and all. Attention and all is beautiful, okay, on that object, but now, right, it thinks that it's a bird. Now, if you had, I mean, if you had, something like prior to that, right, if you had an object detector, which would have done its own job, right, told that, right, okay, right, I mean, this is some animal, right, this is actually, right, a certain animal, a giraffe in this case, then this guy could have used that and not fallen into some bird trap, right. I mean, it could have figured out that, oh, there are only these many objects in this image, therefore whatever word I produce, whatever sentence I produce cannot pick something else other than the objects in the scene, right. So such constraints you can bring in, that's what people do. So that's why I said when you have this one, a detection, object detection network, it doesn't mean that, right, that is a standalone problem. Sometimes you might want to bring that in, right, when you are doing image captioning, because you want to let the captioning network know that, hey, look, right, this image has these objects. You could have missed some, in which case there could be trouble. It doesn't mean that object detection is going to be 100% perfect, right. What if there is an object and it missed it because it was too small? It can happen, or it was occluded, gone. Right. So all kinds of things can still go wrong, but then you won't say a bird, hopefully, right. I mean, you will realize that this is actually a giraffe and so on. So the extensions are like that. I mean, there are many. So it's a whole interesting area, right, where you can where how to marry the two, right, vision and language, in order to be able. And then you have video captioning. Then you have lots of things, and again in video captioning, right, it's about which frames should you pay attention to, because what is the point in paying attention to every frame, because probably there is not much what you see in one frame, maybe the same thing exists in 2 frames here and there. So, right, so basically don't just pay attention to every frame, again attention to which frames, right. So there the temporal thing enters. Now here the attention was on which part of the image, now the attention shifts to which frames in the video,
Which frame, and in each frame
where should be the attention, right. So it just scales up, right, like that. So anyway, right, so there's a lot more. So I think anyway, right, so I mean we can go on and on and on and right, I mean right, endlessly, but then, right, we have to kind of stop somewhere. So with this, right, we actually end the course.